Well, welcome. In this video, you can see we're going to be looking at principles of probability. Now, within these principles, we're going to be using a lot of different terms again, like we did in the previous lesson. So you want to make sure that you're keeping track of these and following along with some of the key words that I talk about. Because part of probability is keeping track of all these key words like or and the word and, situations that are mutually exclusive and those that are not mutually exclusive. So those are things that by the end of this lesson I want you to feel pretty confident with, and if not, make sure that you look back at these notes and refer back to them frequently, because these notes are going to be really important with understanding those concepts. So first, let's look at what I have up above here. We have what's called the addition counting principle. The addition counting principle just finds the number of elements in what we call the union of two disjoint sets. Now, if you're wondering what that word disjoint means, if you skip down to the end of this paragraph, it says that disjointed sets are just another word for what we call mutually exclusive sets, where one does not impact the other. We have some symbols to be familiar with. So you see that little, looks like a U, represents what we say the union of the two sets. So it'd be A union B, or another way to say it is A or B. And or is a really important word when we're dealing with probability, because it means that we're looking at one thing or the other. And means something completely different. We're going to talk about that later in this lesson. So let's look at what we have here with these different probability theorems. The first one is what we call the addition counting principle, dealing with just the number of elements in a set. That's why we use the letter N. We're not talking about probability here. We're talking about the number of elements. We would say that if we're trying to find the number of elements in A or B, and it's mutually exclusive is the key here, we would just take the number of elements in set A and the number of elements in set B and add those two together. Now, if we're dealing with probability, it's the same concept, except for we're using the probability of those elements. So we take the probability of element A plus the probability of element B. If you're confused by that, let's look at some examples. So let's look at this first example. This first example says find the probability the sum of two dice is 4 or 5. Now remember, you have this card with all the different possible outcomes for two dice. So let's look at this card for a second. So again, we're trying to find the probability that the sum of two dice is a 4 or 5. So let's just look at the times that we have a sum of 4. And that happens right here. So that happens 3 times out of 36 times, out of 36 outcomes. Now you notice I didn't reduce that. The reason why is because we have the word or. So we want to find the probability next of having a sum of 5. So we're going to add this probability to another one. So it's best if we keep our fractions unreduced, so that way they have a common denominator so we can add them together. So now let's look at the number of times that we would have a sum of 5. And that's going to happen right here. So it happens 4 times out of 36. So you can see if we add those together, we have a 7 out of 36 chance, and that doesn't reduce, of rolling 2 dice and getting a sum of 4 or 5. Now, it's important to be familiar with some of these terms, like a prime number. You should know that as far as rolling 2 dice, the having a sum that would be prime would only happen if we have a sum of 2, 3, 5, 7, or 11. So now what we could do is we could add those up individually, or let's just look at how many times it happens where we have a sum of prime numbers. So let me erase these. So again, we're looking at a sum of 2, so that would be this paradise. A sum of 3, so that would include these. A sum of 5, which would be those numbers there. We'd have a sum of 7, which would be those. And then we would have a sum of 11. And if we count those all up, we would end up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 out of 36 possible outcomes that are prime. And if you notice, I didn't do this the same as the previous one. I didn't list them out individually, but knowing that I can use the addition counting principle, I can just add up all those prime sums and get my answer that way too. So we would have 15 outcomes out of a total possible of 36 that were a prime sum. And now this one can be reduced. We want to make sure that we reduce that, and we would get 5/12. And that would be your answer. So now that was using, again, the word or was a significant word that we were using. So when we use the word or, that represents mutually exclusive events, because it would be A or B. Now let's look at the word and. When we were using the word and, these are overlapping events. And we have a different symbol that we use for this. So in the previous one, it looked kind of like a U. This is an upside down U. That represents an intersection. So A intersect B would reference the overlapping section of two not mutually exclusive events. So let's look at some examples for these. So this one says, suppose at Edina High School, 298 students study only French, only Spanish, or both languages. Edina reports 115 students study French, and 209 study Spanish. But if you think about it, if you add those together, we end up with more than 298 students. So that means that there's some students that are studying both languages. So our goal is to figure out how many students are studying both languages, and we have enough information to figure that out. Now, I'm a visual person, so it helps me to look at this using Venn diagrams like we saw on this previous page. So on this previous page, since we're dealing with an overlapping situation, we're looking over here on the right, we have some students that are taking only French, so that would be the yellow section. We have some students that are taking only Spanish, that would be the blue section, and some that are taking both of the language, and that would be the green section. And that's what we're trying to find out in this problem. So for example, let's draw our own Venn diagrams here. So let's again call this French, and this Spanish. And the intersection here is taking both French and Spanish. Now, this circle, just this circle on the left, everything here, including that overlapping piece, represents 115 students. Well, if I wanted to figure out how many students were just over here, I would take that 115 and subtract the X that are in both classes. So let's do that. Okay, so again, the reason why we're subtracting is because let's say if we knew that there were 10 people that were taking both classes, that means you'd have 115 minus 10, or 105 students that were only taking French. But we don't know how many are taking both, so that's our X, that's our unknown. So we're going to take 115 minus X, and that'll tell us how many students are only taking French. Well, then we're going to do the same thing for Spanish. Because we know that there's 209 that are studying Spanish, some of those, again, are taking both French and Spanish. So this section over here would be 209 minus X. Well, we know in total that there's 298 students that are taking only French, only Spanish, or both. So if I were to take and add up this section, and if I were to add up this middle piece, and if I were to add up this section over here, I'd end up with a total of 298 students. So here's how we're going to set this up as an equation. We're going to say that those students that are only studying French plus those students that are studying both languages plus those students that are studying only Spanish are going to equal 298 students. So again, if you recognize this is my French students, these are the students that are taking both, and these are my Spanish students. So now let's combine like terms. Now 115 plus 209, we can combine those together, and we get 324. Now at negative x plus x is 0 x's, but then I have this minus x over here, equaling 298. So now I could subtract 324 from both sides, and if I do that, this would still be a negative x, but if I subtract 324 from 298, I get negative 26. So x equals 26. In other words, there's 26 students that are studying both languages. So we were able to use algebra to figure that one out. I'm going to help you with the next one, at least getting this set up. This one says Jamie and Rhonda had to make up their FST test after school. Mr. Murphy told them they could come in no earlier than 3 o'clock and leave no later than 4 o'clock. So in other words, there's 60 minutes that I'm available after school to be with them while they take their test. Now Jamie took 38 minutes on the test and Rhonda took 51 minutes on the test. For at least how many minutes were Jamie and Rhonda taking the test at the same time? So again, we're trying to figure out the minimum amount of minutes that they could have been together in the classroom at the same time. Because if we add together 51 minutes that it took for Rhonda to take the test and the 38 minutes that it took for Jamie to take the test, that's more than 1 hour. So they weren't taking it back to back. There's got to be a little bit of overlap here. So to figure that out, if it's helpful, you can draw a Venn diagram. So we would have Jamie, and we'll have Rhonda. Now Jamie, it took her 38 minutes, but again, there's some overlap, so it took her, so if we call that overlap x, those overlapping minutes, if we took away those overlapping minutes, that's how much time only Jamie was in the room taking the test. And for Rhonda, it took her 51 minutes to take the test. Again, some of that is overlapped with Jamie taking the test. So if we want to find out how much time it took for just Jamie, or that just Rhonda was in the room taking the test, we would subtract her overlapping amount with Jamie. So again, there was 60 minutes available for me to be with these students to take the test. So we're going to add these up and set them equal to 60 minutes. So we'd have 38 minus x represents the time it took Jamie to take the test without, being by herself, plus the overlapping time that she used with Rhonda, plus Rhonda's time would be 51 minus x. So again, this is Jamie, this is their overlapping amount, and this is the time it was just Rhonda in the room taking the test, for a total of 60 minutes available. So I want you guys to go ahead and take a minute, make sure you know how to solve this equation for x, which represents the least amount of time, the least amount of minutes that both Jamie and Rhonda were in the room taking the test at the same time. So go ahead and solve that. So pause the video and hit play when you're ready to check to see if you have the correct answer. So check your answer. You should have gotten 29, so that means for at least 29 minutes, the two students were in the room at the same time taking their test. If you didn't get 29, check your work with mine to see where you made your mistake. Okay. Now, sometimes there's going to be events where we have event A and event B, and there's going to be some overlap. That's what we were just looking at. So here's a formula to help us figure that out without having to draw a tree diagram. So if we want to find, again, these are broken up between the number of elements and the probability of those elements happening. So in the first, you can look at the two formulas and see that they're pretty much identical. Just that one's dealing with the number of elements, again, the other one's dealing with the probability. So all we do is we take and add together the elements or add together the probabilities and subtract their intersection. So when you're working on story problems, the first thing you need to ask yourself is this a situation that's mutually exclusive? Or is there overlap? So if there's overlap, we're going to use these formulas. If they're mutually exclusive, we're going to use the formulas that we saw at the beginning. These here, where we didn't subtract anything because there wasn't anything that they had in common. So with these next story problems, some of these have overlap, some of them don't. So let's look at this first example. A pair of 6-sided dice is thrown. If the dice are fair, what is the probability that the dice shows doubles or a sum less than 10? So I want you to take a second, and I want you to look at your dice card, and I want you to think, is there overlap? What would that look like in this situation? Well, that would be having doubles that are less than 10. Because you have one element that's trying to find the probability that we have doubles. The other element is that we have a sum less than 10. So the overlap is going to be both of those happening at the same time. We have doubles less than 10. And with looking at the card, you should recognize that yes, there are doubles less than 10. So here's how we're going to set this up. So here's what we're going to do. We're going to find the probability of getting doubles. We're going to find the probability of having a sum less than 10. And then we're going to subtract the doubles that are less than 10 because we've counted those twice. Here's what I mean. So looking at your dice card, I've highlighted here all of the situations where we would roll 2 dice and have doubles. So you can see that there's 6 outcomes where that happens out of 36. But if we look at all the times that we have a sum less than 10, so that would be 9 or less, obviously there's some that we're going to be counting twice. So here's how we can use that formula to find our answer here. So we would take the probability of getting doubles, that happened again 6 out of 36 times. There we go. And we would add to that the probability of getting a sum less than 10. And if you counted that up, there were a total of 30 out of 36 outcomes that had a sum less than 10. Now, like I said, we counted some of those twice. There was 4 of them that we counted twice, so we don't want that to happen, so we're going to subtract 4 over 36. And when you simplify that, we get 32 over 36, which reduces to 8/9. So we have an 8 out of 9 chance probability that the dice is going to be doubles or a sum less than 10. Now let's look at the next one. With the same dice, what is the probability that the dice shown is a sum of 7 or 11? So again, for all of these situations, we need to ask ourselves, is there any overlap? If there's not overlap, they're mutually exclusive, so we just add up the probabilities. If there's overlap, we have to subtract the overlap. So with this one, you should recognize that there is no overlap. So what we're going to do is we're going to just add these 2 probabilities together. So the probability of getting a 7, or a sum of 7, plus the probability of getting a sum of 11. And when you look at your sheet, there's a 6 out of 36 chance of having a sum of 7. And there's a 2 out of 36 chance of getting an 11. So 8 out of 36, which reduces to 2/9 is your answer. So here's the deal. I want you to look at these next 2 problems. And I want you to, again, always start by asking yourself that question. Is there overlap or is there not? And then I want you to figure out what the probability of those events happening would be. So go ahead and pause the video, work these 2 problems out, and hit play when you're ready to check to see if you've got the correct answer. Okay, let's see how you did here. So for this first one, if you had a problem with that one as far as getting it set up, the probability of getting exactly 1/3 is 10 over 36. Now, if you got 11 out of 36, let me explain why that would not be. Because it's saying that exactly 1/3. So this one here is where both dice are 3. So we're not going to count that one. So if we count all the other ones, we end up getting a total of 10 possible outcomes where there is exactly 1/3 showing up. So that's why it's 10 over 36. Again, these, by the way, there was no overlap, as you could see from the previous screen. So we're not going to have to subtract anything. So we just add to the previous fraction, the sum being greater than 9 is 6 out of 36. Add those together, you get 16 over 36, or 4/9. And then you can check and see what you should have gotten on the next example. Now, another term, one final term you should be familiar with, is this idea of complementary events. And all that means is that the complement of an event is everything that's not that event. So the complement of event A would be called not A. Or if we look at this theorem, to find the probability of it not being A, we just take 1 minus the probability of event A. For example, let's refer back to the previous example we were looking at earlier, where we had 298 students studying languages, the Spanish and the French languages. If a student is selected at random, what is the probability that he is not studying both languages at the same time? So the way that we could look at this problem is, since we're trying to find the probability of them not studying both languages, we could use this theorem and look at the complement, which would be 1 minus the probability of studying both. Because we found, remember, that there was 26 students that were taking both French and Spanish. So we could take 1 minus the probability of that, which would be 26 out of the 298 students that were taking those foreign languages. Now, again, I'm going to keep this as fractions. So 1 is the same as 298 divided by 298 minus 26 over 298. So all I did is I changed that 1 so we'd have a common denominator. And if I simplify this, 298 minus 26 is 272. So the probability that a student is not studying both languages would be 272 out of 298 students. So that's how we can use a complement to quickly get our answer without having to go back and do repeat a whole bunch of work, or to work with a whole bunch of extra numbers. So that's just a little trick. So using complements can be a handy tool to use in different situations. So that's it. So good luck now as you begin working on the assignment for this section.